All right, everyone get ready because today we are diving deep into some seriously cool stuff.
Definitely cool. Super interesting.
Yeah, remember that letter we got from Stefan?
Yeah.
He was freaking out a little bit, in a good way, about AI winning not just one,
Right.
but two Nobel Prizes this year. And honestly, I gotta say, after digging into the research, I totally get it. This is huge.
I know. And, it wasn't just any two Nobel Prizes. It was the chemistry prize,
Yeah.
and the physics prize. And they're both related to just absolutely foundational breakthroughs that AI enabled us to find.
Yeah, it seems like AI is kind of like the conductor of like this big orchestra
Yeah.
of like scientific discoveries that are happening right now. But what really blew me away, Stefan, was that it wasn't just about using AI as a tool. It was about the foundation of AI itself, right?
Yeah, exactly. It's like,
Yeah.
it's about these fundamental shifts in how we understand how things work.
Yeah.
And I guess we could start with the chemistry prize.
Yeah.
I mean, this year, it was all about proteins. Like designing brand new proteins and then also predicting the shape of any protein, which is a huge, huge deal.
Okay, wait. Time out for a second. For those of us, including me, who maybe forgot what they learned in high school bio, why is knowing the shape of a protein such a big deal? It's not like they're pieces of a giant jigsaw puzzle, are they?
Well, I mean, they kind of are.
Okay.
Think about it. Proteins are like these microscopic machines, and they have these really, really specific jobs, like down to like the nanometer level. So their shape actually dictates how they work. So we're talking about like building our bodies, fighting off diseases, like you name it. It's all about proteins and their shape. Think of it this way. If the protein shape is wrong, it's like trying to fit a square peg in a round hole.
Right.
It's just not going to work.
Okay, so if we know their shape, we know like how they function, basically.
Exactly.
Okay. That makes sense, but that can't be easy to figure out, right?
No, not at all.
I mean, it's not like they're just like chilling there with a measuring tape figuring out the dimensions of these proteins.
Definitely not.
Yeah.
I mean, for decades, figuring out the shape of a protein from its building blocks, the amino acids, that was like the Mount Everest of biochemistry. It was like the ultimate challenge.
Wow.
Because you're basically trying to solve this massively complex 3D puzzle with millions of pieces. And you're doing it blindfolded.
Oh my gosh.
Yeah, it's that hard.
That's intense. And so that's where David Baker comes in, right?
Exactly.
Our protein origami master,
That's right.
Nobel Prize winner. He was basically like, challenge accepted, hold my beer, I'm going to figure this out.
Yeah.
And he came up with this software called Rosetta, right?
Yeah. And, the thing about Baker was he thought, instead of spending years on these laborious experiments, why not use computational power to try to predict the shape of a protein from the amino acid sequence? And Rosetta was that was like his software, his weapon of choice to figure this out. But here's where things get really interesting.
Okay, hit me. I love a good plot twist.
Right. So they're working on this. They realize Rosetta can be used in reverse. Yeah. So instead of predicting the shape from the sequence, they thought, what if we design the protein shape we want and then figure out the amino acid sequence to build it?
Wow.
I mean, it's like this totally groundbreaking idea.
So they're basically like protein architects now.
Exactly.
Like, let's build it. That's incredible.
Yeah.
Did it work?
It did. So in 2003, they created this totally new protein called Top7. Like, it had a unique structure. It was a structure never before seen in nature. This was like a pivotal moment because it proved that Baker's crazy idea, this computational protein design, it wasn't so crazy after all.
It worked.
Yeah, this opened up this whole new world of possibilities.
Wow. So we've got Baker over here. He's like building proteins like a master craftsman.
Yeah.
But then what about like predicting the structure of any protein in existence?
Yeah.
That's where the other chemistry prize winners come in, right? The AI masterminds. Hassabis and Jumper from DeepMind.
Exactly. And this is where things get really interesting because you've got these people coming from these totally different fields. You've got neuroscience, you've got physics.
Yeah.
And they basically came in and kind of turned the protein folding world on its head.
Okay, so we've got these AI hotshots, Hassabis and Jumper, waltzing into the protein world. It's like bringing in a couple of rock stars to solve a physics problem. What was going through their heads?
Well, Hassabis, he was already thinking about how brains learn, with his background in neuroscience.
Right.
And then you've got Jumper, the physicist. He was, get this, interested in simulating complex systems,
Okay.
like proteins.
Oh, interesting.
Yeah. So they kind of brought this fresh perspective, this outsider perspective to this whole problem.
Yeah.
And it really paid off.
And they weren't messing around either.
No, not at all.
Like, they entered their AI creation AlphaFold
Yeah.
into this big protein prediction competition, CASP, which I've heard is like the Olympics of protein folding. Is that right?
It really is. It's
Hmm.
like everyone comes together and they duke it out, to see who can predict these protein structures the best.
And how they do.
So in 2020, AlphaFold 2, that was their updated AI, like the second version.
Okay.
It took home the gold. And I'm talking, it wasn't just like a little bit ahead. It achieved near perfect accuracy in predicting these protein structures.
So they blew everyone away.
They blew everyone away. I mean,
Mhm.
this is something that people thought was impossible, just a few years before.
So wait, so they basically cracked the code, but like what does that even mean for the average person like me?
Okay, so imagine a world where we understand how any protein in nature folds.
Oh,
We can
okay.
suddenly see these tiny little machines in action.
Right.
And this has huge implications for things like drug discovery, right? Because if we can understand how proteins work, we can design drugs that target very, very specific proteins.
So it's like having the blueprint
Exactly.
instead of just kind of like
Instead of just like throwing spaghetti at the wall and seeing what sticks.
exactly. That's a good way to put it. Okay, so this is already like blowing my mind, but it gets even crazier, right? Because this is where we circle back to those physics Nobel winners and how they're connected to all of this. This is where I need like a big whiteboard to follow along.
It's all connected.
Yeah.
Remember how we were talking about how these Nobels weren't just about using AI, but about the foundation of AI?
Yes.
Well, John Hopfield and Geoffrey Hinton are physics laureates.
Yes.
They are the foundation.
Okay. So lay it on me. How did these physics brainiacs pave the way for like AI to revolutionize everything from protein folding to who knows what?
Let's start with Hopfield.
Okay.
So back in the 80s, he was trying to understand, like, how do our brains store and recall memories? It's like one of the biggest mysteries, right?
Yeah, for sure.
And get this, he found inspiration in magnets.
Magnets, like the ones on my refrigerator.
Yeah, like the ones holding up your kids' drawings.
You're telling me those little things are like the key to the human brain?
Well, you wouldn't think so, but think about it. Magnets have these tiny little particles, atoms, and they all align their spins, right, to create this magnetic field.
Right.
And Hopfield saw a parallel there to how neurons in our brains might work, firing or not firing to store information.
Okay, I'm starting to see the connection here a little bit.
Yeah.
But how do you go from like magnets on a fridge to like actual memories?
So he created this mathematical model. It's like this network, right?
Hmm.
And each point in the network is kind of like a neuron.
Okay.
It can be on or off,
Right.
representing like a bit of information.
Okay.
And the connections between these points, kind of like synapses in the brain, they have these different strengths. So it's like one of those light up boards, where you push the pin in
Yeah.
and it turns a light on or off.
Yeah.
Each light is like a memory.
Okay.
And the brighter the light, the stronger the memory.
Oh, okay. That makes sense.
And what Hopfield showed was that this network could store and recall these patterns, even if the input was incomplete.
Wow.
Like how you can recognize a song
Yeah.
from just a few notes, even if you haven't heard it in years.
Okay, so you're saying my brain is like a really complex magnet?
Well, not quite.
Okay.
But Hopfield's work was so foundational for understanding how these networks process information.
Okay.
And that's at the heart of how AI learns today.
Gotcha.
And speaking of learning, that's where Geoffrey Hinton comes in.
All right, so we've got Hopfield and his like magnet-inspired brain networks. That's pretty wild. But where does Hinton come in? Did he have some sort of magnetism epiphany too?
Not exactly magnets this time. Hinton, he was also fascinated by the brain, but he got his inspiration from a totally different area of physics. This time it was statistical mechanics.
Okay, you're going to have to break that down for me. That sounds like another one of those things I should have paid more attention to in school.
All right, all right. It's not as complicated as it sounds. Imagine like a jar of fireflies,
Okay.
thousands of them,
Yeah.
and they're all blinking on and off, right? Statistical mechanics, it's not about like tracking every single firefly. It's about understanding the overall patterns, like how they blink together as a group, even though each firefly is doing its own thing.
Okay, so it's kind of like seeing the forest for the trees.
Exactly.
Okay, I got it. But how does that apply to AI and, robots taking over the world?
Well, Hinton realized that instead of programming every single rule into a computer, line by line, what if we could let the computers learn from the data itself, like those fireflies?
Yeah.
He developed something called the Boltzmann machine, which sounds super complex.
It does sound kind of scary.
Yeah, but it's basically a network that learns patterns from data. kind of like your brains do, right?
Okay.
So instead of like telling the computer, hey, this is what a cat looks like, these are all the exact features, you just show it thousands of cat pictures, and it starts to pick up on those patterns.
So it figures it out on its own, basically.
Yeah. And once it learns enough, it can recognize a cat in like a totally new image.
Right.
It's never even seen it before, but it knows that's a cat. Just like we learn to recognize faces
Mm.
or voices, or even like if a cake is going to be delicious just by looking at it.
Yeah.
It's all about patterns.
Okay, that's really cool. So I bet people were like lining up to give Hinton awards when he first told them about this, right?
Well, actually, just like Hopfield, Hinton faced a lot of skepticism early on.
Yeah.
Back then, people thought these ideas were a little too out there, too much like a pipe dream.
But look at them now.
Right. It's amazing to see how these pipe dreams are literally changing the world. And their physics-inspired ideas, they laid the foundation for the AI that's now predicting protein structures, like we talked about with the chemistry prize.
Oh, it really is all connected.
It really is. And that's what makes this year's Nobel Prizes so remarkable. It's not just about the amazing achievements, but it's about how these deep connections exist between all these different areas that we often think are totally separate.
This whole deep dive has been amazing. We started with proteins and went to magnets, then fireflies. Stefan, you really sent us down a rabbit hole with your question, and I loved it.
Me too. It really makes you think,
Yeah.
this is just the beginning. And now that we have these incredible tools, these AI powerhouses built on physics and pushing the boundaries of chemistry, who knows what we'll be able to discover next?
Exactly. It's not just about having all the answers. It's about what new questions we can even ask now.
Totally.
So what will you explore? What mind-blowing AI-powered adventure will you go on? Keep those questions coming because we'll keep diving deep. Until next time.